All right, back to the normal curve that you guys did some videos on. That the same work that the sub was supposed to be monitoring, but I came in on Monday. This is a normal curve. Picture this distribution created by millions and millions and millions of pieces of data. For instance, like the average height of all people in Texas. If you did a histogram and put million data in your calculator and did a histogram, it would form this nice, perfect curve. Put the SAT scores of everybody in South Texas in a calculator. Do a histogram of everybody's SAT scores. It would produce a nice, pretty, normal curve. Anything that you can quantify, weights, put all your weights in. Put all your heights in. Put all your length of your fingernails. It doesn't matter. As long as you're talking about a large population, it'll always create a normal curve. Moving on here. Looking at a nice, beautiful normal curve. We are going to use this no calculator for the rest of these problems. We're going to strictly use the areas found under the curve. If you watched one of those videos very carefully, there was a person who told you that this center of this curve is your mean. Because we're talking about a large population, we're not going to use X bar for mean. We're going to use mu. Mu. The same symbol you used in physics for the coefficient of friction. And then we're not going to use S for standard deviation because this was for a sample. This is a large population. We use sigma. So if I add 1 sigma to mu, 1 sigma, there's sigma. I can add 2 sigma, 3 sigma. Could I add 4 sigma? Yes, you can. You can, but who needs to? Who needs 5 sigma? Only if you're Shaquille O'Neal are you out here for your shoe size. Yes, Shaquille O'Neal might be out here. He is such an anomaly of adult men. But we're going to talk about how important 3 sigma is. To the left, 1 sigma to the left, so I go negative 1 sigma, negative 2 sigma, negative 3 sigma is all we need. When I say sigma, it means standard deviation. Okay. Between 1 sigma to the left and 1 sigma right, that adds up to, do you remember the magic number? 68% of all data will fall there in a normal population. If you have the values all the way to 2 sigma, and you go from negative 2 sigma to 2 sigma, the percent of data that falls in there was, who remembered?
13.59 for each side.
Well, you're breaking it down. The total area is just 95%. I know what she's getting at. She's hitting it on the head. If you needed to go to 3 sigma, way out here, look at, there's hardly anything left there. To positive 3 sigma, that area is 99, well, we round it just to 7% in the, we're doing the empirical numbers. These are the approximations that get your answers pretty doggone good. Not perfect, but it doesn't have to be. Now, you saw what Julia was already doing. Let me erase most of my work here. I hate to do this. It was so much thought into this. But I am going to leave the 1 sigmas and 2 sigmas and all of that. What Julia was saying is that if you knew that between 1 standard deviation left and 1 standard deviation, if you knew this was 68%, then how much would the tails be? This tail and this tail. How much would they have to add up to if the middle was 68? Reminding you that it's a density curve and the area under the curve is 1. 32. Did you hear Julia say earlier 16%? Where's 16 coming from?
I said 13.
Oh, 13. Oh, okay. I thought I heard you say 16. So, if these two in yellow are 16, what's the value of 1? I'm sorry. If the 2 tails are 32, what's the value of 1? 16%. They both are 16%. 16% to the right, 16% to the left. If you were to go to the second standard deviation, and we know that everything on the inside, let me get rid of some of this inside junk. Everything on the inside now is 95% from here to here. All of this is 95. Well, then tell me what's the area of the green tails have to add up to? 5. Because 5 plus 95 is 100%. Then what's the area of 1 tail? 2.5%. Both of them are. Now, God forbid that you have to go to 3 standard deviations out, because all of this is 99.7, and I get kind of confused when I talk about that big of a number. 99.7 between the goalposts, 99.7%. What percent is these red tails adding up to? Say it again.
0.135.
Well, one of them or 2 of them? Oh, well, okay. And you're giving me, again, I think you're giving me well, isn't 100% minus 99.7 equal to 0.3? Don't both of those add up to 0.3 in this rule?
Yeah, but if you go to decimal, then it's 0.27.
Oh, you're using a calculator. Yeah, remember, we're not using any calculator. We're doing by these estimated answers. So half of 0.3 is actually, well, let me rewrite that. Half of 0.3 is 1.5%. Very small. 1.5%. By the way, is 0.015. That's very small. Well, how do I use these math? You start out with the mu, 1 sigma, 2 sigma, 3 sigma.
Yes, it asks for the third one.
Did I look at the number wrong? Oh, z-scores. And right now, the only thing I'm going to tell you about a z-score, I'll give you a very simple definition.
Yeah.
The z-score, z is the distance. A value is from the mean. And it can be positive or negative because you can be on both sides of that normal curve. Here's your mean. And some of the common values that we've already used was z is equal to 0. That means if z is equal to 0, it's exactly the same as the mean. Z equals to 1, take a guess. How far away from the mean is it? It's 1 standard deviation away. 2 standard deviations away. 3 standards, so that'd be z equals to 3. Z could be a -1, -2, -3. Z could also be a -1.4. Is that right? Z could be a negative, that would be over here. That would be right here. Right now, you haven't really done a lot of problems except for that one worksheet where you all cheated and used the calculator and did the normal CDF. Z could be a -1.4. So why do we need Z? I'm going to give you a good example. Here at our school, it is possible that 4 Algebra 2 teachers can give a test to each of their classes, and let's say it's on exponential functions. Not all teachers are the same. They're all writing their own test. I wrote a test with 100 points possible right here. So I'll put my initial here. C, that's me. I wrote a test and I decided to give you 50 questions, each worth 2 points each. And the student that was randomly picked from my class got an 83. Now, Mr. Ramos, he decided to write a 15-question test worth 3 points each. That's why it's worth 45 points. And his random student scored a 37. Mr. Jabs, if you ever had Mr. Jabs, he handwrites every test, and they're not multiple choice. They're all open-ended. Show your work for every problem. And he wrote 9 questions to test you on exponential functions. 9 questions. They were 2 points each. So that's 18 points. His random student scored 15 points possible. Miss Schneider, she found 75 multiple choice questions that she liked. So she gave you 1 point each. So her test was bigger, and her random students got 63. By looking at those, can you tell me who did the best?
63.
Why? Mine scored 83. Why wouldn't mine be the best?
Because you said 100 and 63 out of 75.
That's true.
So you said the 63 was out of 75, so you are wanting to turn that into, why am I doing that color? You're wanting to take 63 out of 75. What grade would that give you then?
Actually, no, because it'll be Miss Schneider because she calculated it.
What's that?
Oh, no, never mind.
She would calculate it?
If you do 63 out of 75, you get an 84.
And if you do yours, then it's an 83.
Okay, mine stays an 83%.
Miss Schneider's is an 83.
Hers turns into an 84, so it looks like the person did better in Schneider's class, right?
Yeah.
How about in Mr. Ramos's class? What are you going to do?
Wait, is that, oh, no,
82.
that's the second one, 82.
82.
37 out of 45 was 82%.
The third one was 83.
And Mr. Jabs, 83%. So now can you decide who did the best? Miss Schneider's student did the best with 84, so that student D did the best. Who did the second best?
Yours.
Yeah.
Two.
Not really. Do the math again. 15 divided by 18.
That's 83.
Well, is there decimals?
It's
83 repeating.
yeah.
83.3333? Isn't that better than 83.0? Who did better? Jabs. Then mine, and then Mr. Ramos. So, are you convinced that this kid is the best kid of everybody who's taken Algebra 2?
No.
No.
I think the teacher is.
What?
The teacher.
Even the teacher has, so she's the best teacher. That's why this is the best student, right?
Well, it's
So-
also highly selective, so it does not necessarily be the best.
Are there other variables involved?
Yeah.
Sure there are. That's why when you go and get your award at the end of the year, you're okay if Miss Schneider's student got the award, right?
Well, no.
No, why not? They had the highest average.
Yeah, but
That's how we do it. We all submit our highest average to the team leader, and then the highest one there gets the award.
what's it called? Who gives harder tests?
Oh, you think there's a difference in tests?
Yes.
So you think it's better to judge the person based on just that teacher?
Because if they all follow the same curriculum as well, they're all the same teacher, and they all theoretically got the same class.
So you want to judge each on their own normal curve?
Yeah.
Wow.
Because that's how.
That's in a perfect
it would be
society.
fair.
That's in a perfect world, but why don't we become a perfect world?
But it takes some-
That's exactly what we're going to do. That's the z-score. The z-score, as I mentioned, is the distance, and it's a number of standard deviations away from the mean. The lower the z-score, whether it's positive or negative, absolute value is the lowest, is closer to the average. Your formula, might want to write this down, is always going to be x, which stands for your score, minus the average of the scores. All of that is divided by the standard deviation of all of the scores. Negative z implies that you did less than the average. A positive z meant you did better than the average, unless you were running. If you're running, you want a negative z score for your time. You want a lower time. If you're playing golf, nobody wins a golf tournament by scoring 100. They'll win the golf tournament if they score an 18, a hole in one for every single holes of 18 rounds of golf. The closer to 18 is probably better than closer to 100. So negative and positive is relative. So let's take these same students and let's look at the class. In my class, it was found that the class average was 75. And look how huge my standard deviation was. 10. Remember, we talked about that. That may not be a great thing to have a high standard deviation. Look at Miss Schneider's. Her class average was a 92.4. And her student got, this student got a 98. And the standard deviation was 6.3. So standard deviation has a lot to do with how you did in that class. So we are going to use the z-score formula for every class, for every one of these 4 students. First one, z is equal to the score, 80, minus the mean of the class, 75, that's why it's called x bar, all divided by the standard deviation of 10. That I can do in my head. 80 minus 75 is how many? 5 over 10 is how many? 0.5.
Wait, so what's the formula? C equals score.
You see it here? It's the value of the score we're looking at, subtracting the mean of all of them. All of that divided by the standard deviation. So at 0.5, let's see if I draw a picture here. Let me draw a normal curve for a second here. And label my z-scores of 0, 1, 2, and 3. My student scored a 0.5 z. So where would I label him or her? If z is 0.5, it's better than 0, but not as good as the 1. So it's probably here. You agree? Now let's do, who teaches the class B? That was Mr. Ramos. So let's do Mr. Ramos's student. Z is equal to the 28 minus the 25, all divided by 4. 3/4, what's that decimal?
175.
So Mr. Ramos's student actually did better than my student, because on the normal curve, compared to his competition in the class, he did better against all the other students that took his test. So that student really did better in his class than my student did in my class. Let's do Mr. Jabs. Z is equal to 13 minus 12, all divided by the 1. How much is that? 1. Mr. Jabs' student did better than either of Mr. Ramos and mine. You see that? So the farther right on this curve, the better you did above the average. That's more standard deviations away. That's a higher score than everybody else. Let's do Miss Schneider's. Z is 98 minus 92.4 divided by 6.3. This one I cannot do in my head.
It's point eight.
Point what?
0.8888.
88888. So I'll just say 0.89. Which means, oh, wait a minute. That means she's even closer to the 1. She's actually better, right? Oh, I'm sorry. Let me fix that. She's between me. She's between Jabs and Mr. Ramos. So, which student really did the best? Wow, I knew he was the best teacher. C. Who was next? Oh man,
So you're last.
I'm last. Third place was Ramos. B. Yeah, they're gonna fire me.
So you put Schneider as last.
Maybe that was unconsciously. I did that on purpose. I should have wrote a what? Me. I didn't want to put me. Oh well.
Watch the next time you change it. You're gonna change it to D, and then I'll give you Justin.
Yeah, I'll be that teacher. Yeah.
I don't know, it's gonna be the worst. I mean,
But actually, I picked it based on. I actually do give 100-point tests, so that's the reason I grabbed it. And Mr. Jabs really does write his own tests, so he's not going to write 100 problems. You see? So I tried to match it up. Mr. Ramos could have gone with 100 points too. But anyway. So remember, this only works when the distribution is normal. Obviously, the Z is all about the normal curve. So let's look at another scenario. A race in the New York Marathon. And they randomly picked 4 runners. I'm not sure, how they randomly picked it, but runner A was a man between 25 and 35. Runner B is another runner, male, from 36 to 45. C was an old man. This is more my division. Age 50 and higher. This is where the old people go. They're going to think I just dropped over dead. The 4th person was a young female, just as young as this young man over here, 25 through 35. We have their times that they did to finish this race. Look at the runner A. Why is it not working there? Runner A finished the race in, that's not doing it real, 2 hours and 45 minutes. whereas the female took over 3 hours. So it sure looks like this young man is a better runner than this young woman because he came in before her. But he's not as good as the men. Look at the two other men. Even this old man came in. Oh no, he came in 3 hours and 39 minutes. He's not looking too good. And this older man came in after this man, the younger man. So I'm looking at the standard. The average was 3 hours and 2 minutes. Look at the averages of these races. The average of the old men was 4 hours and 27 minutes. And he listed the standard deviations in minutes. We need to have all the units in the same. So is it easier to convert minutes into hours or hours into minutes? You don't want to do like the 19 minutes into hours? Wouldn't that just simply be 19 divided by 60? Yeah, or a decimal, right? What's the decimal? 0.316. You don't want to use that and to change those minutes to hours and change those minutes to hours? You don't want to do that? You'd rather go to minutes? Fine. Then what is 2 hours worth?
120 minutes.
Add that 120 to 45. What does that become?
165.
165 minutes. Let's do the average of that race. 3 hours is 180. Add it to 2. All right, you're right. This is easier. 2 hours added to 59. 179 minutes. 3 hours added to 23. 2 what? 19 minutes. The senior division, 3 hours is 180 added to 39.
Never mind, sir.
Is-
That one's 219.
This one's 219? Oh, what was this one then? Somebody tell me.
203.
203?
Yes.
4 hours and 27 minutes would become? Well, 4 hours is 240. 267 minutes. Oh, I never did the runner D. 3 hours and 1 minute would have been 181. 3 hours and 41 minutes? 221 minutes. Okay. So in order to really say, I mean, I can say that these men were, or at least these two men were better than this female. And it's obvious this young man came in before this female. But remember, when you run, they give you medals and trophies based on your division. I mean, you're only running. One time I was running, and this old lady, I mean, she had to be 20 years older than me, was passing me. And I was like, what? Thank God I'm not in her division. Guys, she beat me. And she wasn't even making a sweat. She was good. That's okay though. Now, and so let's do the Z-score. Let's normalize it. Let's standardize every one of these runners. It's called standardizing it into one system. Like you turned everything into percents. That was fine. That was a standardization in a way. But then they were all in percents. But this young man over there said some teachers' tests are harder. So let's just rate you based on how you did with that teacher. Well, let's rate you how you did with just the runners that are men between 25 and 35. So Z will equal to the time, 165, minus the average, 182, divided by 16.
Sir, is it going to be negative?
It could be, is it?
Or do you do 182 minus?
No, you always do your score minus the average. That does come out negative. Thank you. Negative what?
1.0625.
1.06. I'll just put 0.6. What does that imply if it's negative? He ran faster than the average person in that division. That's a good thing. Negative doesn't always mean bad. In this case, it's good because it's his time. He wants a smaller time. Let's do the next z-score. That z would be 179 minus 203, all divided by 19. That also is negative. Negative what? 1.26. So if I compared these two men, which did better?
1.26, the 362.
Yeah, the older man actually did better than the younger man, even though his time is longer. The younger man came in the finish line before him, but he was not the fastest of all the young men. This older man was faster than this younger man. Not faster necessarily. I didn't say faster. I shouldn't say that. He wasn't faster, but within his group, he was. All right, let's do the old man.
The old man is really nice.
His z was 219 minus 267, all divided by 28. That's also negative. 1.71. He is far to the left. Think about what these numbers are saying. This is almost a -2. This isn't even close to a -2. This person isn't close to -2. This one's not even at a -1.5. This person did wonderful in his group. He's very competitive. Let's see how she did.
So, like, for a half marathon, it's usually like, well, I do like 2 hours and 20 minutes.
2 hours and how much?
20.
Oh, that's awesome.
Like, that was my first one. It was like 2 hours and, like 11 minutes.
That's really good. You said your first one.
No,
I mean, that's 20 something miles, isn't it?
No, it's 13 miles.
Oh, you did half marathon.
Yeah, half marathon.
Oh, 2 hours?
Yeah. For half. But, and that's wait a second.
Did you finish standing up?
Yeah.
Then you're a winner. Yes. You beat everybody who was laying on the couch that day. Okay? Equals, next one, 181 minus 221. It's what? Which one? Oh, you already have the answer? Is how much? Oh, she did better than... Who was the better runner? Yep. Well, let's be politically correct. She's a woman, right? She's 25 to 35. Okay. So, guys, back up here. Runner D had the best time. Runner C was next. Then B. Then A. Estefania, did you get these the ratings? Did you get the best runner? Better be in your notes. All right. Let's look at comparison of two baseball leagues. Let's compare the American Baseball League players versus National League players. And what we have is there are two baseball leagues in the United States. We have their means and we have their standard deviations. Letter A says Jim Thone. I don't see I thought there was an R in it earlier. Played in both leagues and had a batting average of .27, but actually .277. This was in the American League. Then he had a .273 in the National League. Show work to determine what league his batting average was higher compared to the rest of that league. So it sure looks like he was a better player in the National League. But are there other variables? Yes. I'm sorry. If everybody's get the hall pass there. 277. No, he actually was better in the American League. Or was he? Maybe the National League had tougher pitchers. Maybe the players in the National League were slightly better that he was playing against than the players in the American League. You know, the pitching really makes a difference how you hit the ball. So let's do both. Let's normalize both of them. Let's normalize both of them. Let's do Z of the American League. So what was his score in the American League? 0.277. What was the average of the American League?
0.263.
And the standard deviation of the American?
0.0202.
0202. Somebody calculate that.
160.
Say it again.
169.
0.69. So he did better than the average player. Not quite, more than a half standard deviation, but not even quite 3/4 of a standard deviation above. I'm not saying it's bad. What do I know? Let's do his normalization in the National League. His score in the National was 0.273, was it? And the average of the National was? Point what? I can't hear anybody.
Wait, the what?
The average of national
The-
is 0.254.
25254 was the National. Standard deviation of National?
0.0214.
Final Z score is
0.88.
0.88. If I just take two decimals.
Oh,
So even though he had a higher league, I can take 3 or 4. Normally we use 4, but we're just trying to prove a point here. He did better when he had a higher average in the American, but against his peers, he was a stronger batter in the National League. That's pretty close to 1 standard deviation above. All right. We got the next problem is another person, Aaron Rowan. He played in both leagues. Go ahead, take 5 minutes to get those two. Or, you already have them? Somebody already has them already? You do. Oh, okay. I thought you had them. Go ahead, take a few minutes. I'll wait for your answers. You do have them. Margot, why are you on fire? You even have it written down? The work too? Or just the answer? Yeah, you know how much I love just answers. But I guess we'll just compare everybody's answer with yours, Margot. Got 2 people done. Let's see, how did he do? Yes. You have it too?
Yeah.
Okay, he had a 0.25 in the American, and he had a smaller average in the National. So it looks like he was a better batter in the American League, but are the averages deceiving us again?
He was lower than the
Oh. So
and the person too.
Z-score of the American League was what? 0.64. Oh, so he's not even as good as the average in the American League. And in the National League, his Z-score is? Point what?
Negative 0.61.
61?
Negative 0.61, yeah.
So, all right, so, okay, so this is a random person, played in both leagues. He's not as good as, obviously, Jim Thone was. But which league did he do better in? He did better than the Nationals, even though his batting average for the American was still higher, wasn't it?
It's or like if we do this on the quiz, we just put like do we round it or do we put like 4 decimals?
You'll never be wrong if you do 4 decimals.
So for this one, so
But you prefer round
that's
it,
higher.
No.
So negative 0.64 is worse than 0.61.
Look at it on the normal curve. Here Z is 0. Here Z is a -1. So the American, he's at 64. And the National is at 61. So they're both bigger than halfway there. But because the American was farther left, he did worse in that league. What's that? You have the next answer too? Wow.
That's positive is better.
What's that?
Positive is better.
In this case, not in the running speeds. In the marathon runner, you want a lower time, right? Okay, the last one here. And Margot already had it done in her head almost, so it can't be that bad then, but I thought it was a tough problem. If a player plays in both leagues and he bats a 300, that's called a 300, 0.3000. We call that batting a 300. In the National League, show appropriate work to determine the average that he would have to have in the American League so that the average would be the same compared to the rest of the league. So you can't say just a 300 again to have the same. So this is not the same kind of problem. I'm very curious. Margot, are you confident enough that you could put it on my recording? No?
No. I'm pretty sure, like, I see, like, a mistake right now.
Oh, you saw a mistake already.
Yeah.
So all I have right now is some information about what his score was. What would I need to find out with this 300 in the National League? What would I have to figure out? Maybe what the Z-score was? Yes? Am I alone? Let's find the Z-score of the National. He scored a 300.300. What was the average of National again? 254. What's the standard deviation of the National? 0214? No, I'm starting to hear the standard deviation. Is it 0.0214? Okay. So his Z-score is how much? Louder. 2 point? Woo, 2.1495. What does that tell you about the Z-score being a 2.4? This is 0, this is 1, this is 2, this is 3. Where is he at in the National? He's here. So we want to find out what his batting average must be in order to be just as good as he was in the National. So what do you think I do with this z-score? You guys know algebra. What am I missing in the equation of this z-score formula? I don't know his score, do I? Do I know the average of the American? Do I know the standard deviation of American? Do I know what z I want? I want the same z. So why don't I do that? I don't know his score, so I'll call it x. Minus the average of the American. What's the average of the American League? 263. What's the standard deviation?
0.0202.
Must equal to 2.1495. Isn't this just basic algebra? How would I solve it? Let's do the steps in our head.
Multiply with 0.202
By,
to the top, and then
okay, then?
repeat it to the other side,
Then add this to the other side.
and then add that.
Yes. So please, do that math in your calculator real quick. You can pick up your calculator and just type it in and find out what x has to be. All of you should be doing it. That'd be a very good warm-up problem next Friday.
It's 2.413.
To what?
2.413.
0.214.
0.413.
Where's the decimal at?
After 2.
No, it can't be. His batting average has to be.
Wait. I think. Wait.
You think you got it?
Yeah. Wait.
Yes. We take this number times this denominator. That gets rid of it over here. Then all I have to do now is add this number to this answer here.
It's 0.38304.
0.38304.
Yeah.
There you go. See you guys on Friday. No extra homework.